Kumar Das. So I'll handle this session. So in this session, actually, we are going to discuss about the optimization method, especially the non-traditional optimization methods. And I will put more emphasis on the genetic algorithm. But before that, let us understand what is the need of optimization method. Then we'll see with some examples. We'll understand some applications also. We'll see some of applications related to the genetic algorithm. So this is the agenda. First, we'll see the some of the basics related to the optimization method. Then we'll discuss about the genetic algorithm. So if you see problems related to science and engineering, earlier the problems are very simple. So people used to model these problems using linear programming or dynamic programming techniques. And basically, we model the problems in the form of variables, and we see the dependency between different variables, and we solve the problem using some of the well-known methods. But when you come to very large scale scientific engineering problems, the traditional optimization problems is failed to address such type of problem. The main reason is that when you go for big problems, you have a very large number of variables, which is very difficult to manage. And to calculate anything, you require so many dependencies and so many equations. So it is very difficult for anyone to solve the problem. Moreover, the objective functions that are used in such type of problems, they are non-linear. The problem with nonlinear objective function is that when you go for non-objective function, you will see, suppose you find a solution for a particular problem, you cannot claim that particular problem is providing you global solution, right? It may be a local solution, but you cannot ensure that the problem is providing you, the solution is providing a global solution. So in order to overcome the problem associated with such type of problem, we come up with the solution that is called as non-traditional optimization algorithms. So in this non-traditional optimization algorithm, you will get the solution which is very close to the optimal solution. For example, optimal solution is 5, then you will get the solution close to 5. It may be 4.9, it may be 5.1, it may be 5.001, and so on. So let us understand that what is the difference between linear objective function and non-linear objective function. So here you can see the picture shows about difference between the linear and non-linear. Linear is more or less related to the lines, right? So like if I draw a line, then you can say when the x value is increasing, y axis value is increasing. Or if x value is 1, then y value is 2, right? So it is more or less, it is related to a line, right? So you can find a relationship between the x coordinate and y coordinate. So such type of objective functions are linear, and there the optimum is always attained at constant boundaries. Another advantages you can find here that the local optimum solution is equal to the global optimum solutions in the case of linear objective functions. But when you go for non-linear objective function, as I said previously, the local optimum solution is not necessarily the global optimum solution, and the optimum may be in the interior or it may be at the boundary of the constraints. So rather than focusing on a line, in non-linear we focus on a curve, right? So earlier problems are more or less non-linear objective functions. So solving non-linear objective function is very much challenging, right? Because you may reach to the local optimum solution, and you are claiming that you have reached global optimum solution, but actually it is not a global optimal solution. Then if you go for this non-traditional optimization methods, you will see most of these methods are inspired from natural phenomena. Like some methods are biology inspired method, some methods are based upon nature, some methods are based upon how a bird collects the food, some methods are based upon, you can say, related to the ant, right? So different type of methods you will find by looking into animal behavior, human behavior, and so on. And if you look into these optimization, mostly these optimizations are called as stochastic optimization because they use random numbers. You go to any optimization method, you will find that there is a randomness in that particular problem. Stochastic means we want to say that is a randomness there in the problem. Like you want to generate a random number in between 0 to 1. So that random number you want to multiply with a particular function, right? So that value is not known, right? If you iterate now, then you may get the value as 0.5. If you iterate after some time, you may get the value as 0.1, 0.34, 0.78. And many things may happen, right? So the working principle of such optimization algorithms are combination of two extremes. So one is called as random search, which is called as extreme exploration. Another one is called as hill climbing, that is called as extreme exploitation. So there is a trade-off between these two. You have to focus on global search as well as the local search. So when you take a large search space, you have to see your solution should be there in any place. So you have to perform the global search as well as local search in order to achieve the global optimum. So exploration exploitation is always a trade-off in the non-traditional optimization methods. Now, if you look into major groups of these optimization algorithm, you will see that basically three different classes we have divided here or groups. One setup is called as evolutionary algorithm. Some of the examples is called a genetic algorithm, genetic programming, evolutionary strategies, differential evolution, bacteria foraging optimization, artificial immuno algorithm. These all are, this is not the complete list. So you can find a lot many algorithms if you go to the literature, and day by day, number of algorithms are exponentially increasing also. Another set of algorithm you can see, they are called as swarm intelligence algorithm. The popular algorithm like particle swarm optimization, ant colony optimization, or artificial bee colony optimization, shuffled frog leaping optimization, firefly algorithm, glowworm swarm optimization. These are part of swarm intelligence, examples of your swarm intelligence algorithm. There is another type of algorithm which is available, that is called as nature inspired algorithm, other nature inspired algorithm. You will see some of the latest development in this group, like you can see teaching learning based optimization, which is based upon the classroom teaching, and Joya algorithm, which is an advancement over this teaching learning based optimization. If you go for teaching learning based optimization, you may find two different phases, but when you go for Joya algorithm, you will find both pages are merged into a single page. Similarly, in 2020 during COVID time, another set of algorithm is available. One is called as RAW 1, RAW 2, RAW 3. These are the three variants of our algorithm, which was proposed by Professor Rao from SBNIT Surat. Apart from that, other methods like simulated annealing is a very quite old method which belongs to this particular group. Harmony search, cuckoo search, cross entropy, central course optimization, charge system algorithm, grenade explosion method, biogeography based optimization. These are the very popular method in this particular group. So in this lecture, we want to focus on the first group only, that is related to the genetic algorithm that you can apply to solve various problems. So the concept of evolutionary computing is not new. It was quite old. So it was, you can see, developed by I. Reichenbach in the year of 1960. So you can see around 60 to 65 years back. After that, after the invention of this evolutionary computing, genetic algorithm was proposed by John Holland in the year of 1975. He was affiliated to University of Michigan, and soon after genetic algorithm, people try to apply in their respective field. The first application found in the field of structural engineering, or you can say civil engineering, by Goldberg and Samtani in 1986. So the idea behind any type of optimization algorithm is to uh, either to maximize a particular problem or to minimize a particular problem. So the aim of any optimization algorithm, you have to look into the objective function, and by objective function, you have to think whether to maximize it or to minimize it, right? For example, if I consider a set A, and set A consists of five different elements, 1, 2, 3, 4, 5, and I'll take a function f of x, which is equal to x square. And this x value you can take from this particular set A. So if you take f of 1, which is equal to 1 square, f of 2, which is equal to 2 square, which is 4, and f of 3, it is nothing but 3 square, it is 9, f of 4, it is 4 square, which is equal to 16, and f of 5 is equal to 5 square, which is equal to 25. So you have to find an element x0, right? In this particular set, x0 may be 1, 2, 3, 4, 5, any value, such that this f of x0 is less than f of x for minimization for all x belongs to A. So if you look into this particular solution, you can say the f of 1 value is less than all other values, right? You put 1, you put 2, you put 3, any value here, that value is greater than equal to f of 1. So what you can say, so this x0 is the lowest element, okay, or the element for which the value is minimum. So if it is a minimization problem, so in that minimization problem, the best value you will get, that is in the case of 1. But if you go for a maximization problem, then you can say f of any value which is less than equal to f of 5, right? So f of 5 value, which is 25, which is the highest value, okay, you put any value here, you will get always the value is less than equal to 25. In such a case, we deal with the maximization problem. So optimization method means either you have to maximize it or you have to minimize to solve that particular problem. Now there are some important discussions related to the genetic algorithm, because first step of the genetic algorithm is you have to perform encoding, right? Or you have to go for chromosome representation. So for chromosome representation, you have to take a set of variables. So the first question arises here, that how variables in genetic algorithms are encoded, right? Suppose you will take a particular problem, right? Let's say assignment of 5 different works, W1, W2, W3, W4, W5. These are 5 different works that you want to assign to two different uh, computer systems, right? Let's say machine 1 and machine 2, right? Where W1 can be assigned to first machine or it can be assigned to the second machine. So if I represent it in the form of chromosome, then I'll take 5 cells. First one is W1, second one is W2, W3, W4, and W5. Suppose I'm writing 1, 2, 1, 2, 2. So it indicates that W1 should be assigned to machine 1, W2 assigned to machine 2, W3 is assigned to machine 1, W4 is assigned to machine 2, W5 is assigned to machine 2. So in this way, these variables are encoded in genetic algorithm. So in your respective research domain, if you want to apply genetic algorithm or any optimization method, so first you have to focus on the encoding part. Then This is not only the solution, this is one of the solution. If I want to go for another solution may be 2, 1, 2, 1, 2. Another solution may be all 2. Another solution may be all 1, right? These are all variety of the solutions, right? So how to know out of these four solutions, which solution is better? For that, you need fitness function. If I calculate fitness of each and every solution, so based upon the minimization, suppose here you are getting the minimum value, then you can say, yes, this S1 is the having minimum value. So its fitness value is better. It is a maximization problem. Suppose maximum value you are getting in the case of S3. Let it be 1, 2, 5, and 4. So maximum value you are getting in the case of S3. So you can say for maximization problem, solution 3 is a better solution. Now, in the case of genetic algorithm also, we have a couple of selection methods through which you can select some chromosome, you can discard some chromosome based upon the fitness value or based upon different methods. Some of the popular methods are called as Rowland-Hill method, Boltzmann selection, tournament selection, and steady-state selections. We'll discuss these methods through a numerical example. Now, coming to another important discussion here, that population of the mating pool. Like in genetic algorithm, you have to pick two different chromosomes and you have to perform crossover in order to generate the children. So this is called as the process of reproductions. Like you consider one chromosome as male chromosome, another chromosome as female chromosome, and make the crossover to say that this is children 1 and children 2. So in order to perform reproductions, you can apply variety of operator. They are called as the inheritance operator that you can apply to the mating pool. That is nothing but a group of population. Okay, so randomly you have to pick two chromosome and you have to apply this inheritance operator, right? So which inheritance operator you want to apply for a particular problem, that is also very much important. Now there are some questions related to the genetic algorithm. Like somebody may ask you, given a particular problem P, does optimal solution exist for this problem or not? Right? Does an optimal solution exist for the problem P? So your answer may be yes or no, right? If the optimal solution exists for this particular problem P, the next question may be, is it a unique solution or not? Sometimes you are getting the solution, but the solution is not a unique solution. Because in different methods you can solve that particular problem, different values you can get for that particular problem. And what is the procedure to get the unique solution or optimal solution? Similarly, one question may be how sensitive the optimal solution is. Okay, like the solutions are based upon some input parameters. If I slightly change some parameter, okay, is it going to affect my solution or not? That's why they're asking how sensitive the problem optimal solution is. Similarly, another question is related to how solution behaves for small changes in parameter. If the parameter is slightly changed, it is up or down. So whether it is affecting my original solution or not. So that these are the different questions associated with the genetic algorithm, which you have to address before applying genetic algorithm in your problem. So the main concept behind the genetic algorithm is that genetic algorithms are good at taking larger, potentially huge source spaces and navigating them, looking for optimal combination of things and solution which we might not find in a lifetime. So first, before applying genetic algorithm, you have to decide that whether genetic algorithm is applicable for my problem or not, right? That's why if your state source space is very large, source space means you can say all possible solution for a particular problem P. If all possible solutions, okay, all possible solutions, okay, if getting all possible solution is feasible, then you can say that the problem is very simple. but getting all possible solution will take entire lifetime. Then you will say, no, this is not a feasible solution, right? So in that case, you can apply the genetic algorithm. One of the example I'll tell you, like if you consider 512 number of tasks and 16 different machines. If I ask you how many ways you can assign these tasks to the machines, what is your answer? How many ways you can map these tasks to the machines? Any task can be assigned to any machine, right? If I ask you how many ways you can assign these 512 tasks to the machines, what is your answer? Can anybody answer? How many ways you can assign 512 different tasks to the 16 different machines? So it is 16 to the power 512, right? If you solve it, you will get 16 to the power 512. So 16 to the 512 is a very big number, right? And obviously this value is much greater than 10 to the power 512. Okay, because 16 to the 512, if you type in a calculator, you will get an error, right? So if you see 10 to the power 512, which is much lesser than 16 to the power 512, so 10 to the power 512 is nothing but 1 followed by 512 number of zeros, right or not? This is nothing but all possible solutions. So if each solution takes, let's say, 1 millisecond time, each solution takes 1 millisecond time in computer system, then this much solutions will take 1 millisecond into this solution. So if you calculate this one, you will see you will not find the solution in your lifetime. So there you can apply the genetic algorithm. But for a particular problem P, if number of possible solutions, if you see number of possible solutions is, let's say, only 10. So it is very small. So in that case, you cannot apply genetic algorithm. So before applying genetic algorithm to your respective field, you have to decide which solution. Okay, which is you have to decide that whether your source space is small or large, right? If your source space is very large, then you can apply. But your source space is very less, like your number of solution is 10, then you should not apply genetic algorithm. And there are three most important aspects of using genetic algorithm. First one is called as objective function. Second one is the genetic representation. Third one is called as genetic operator. Generally, objective function we are used to we are using objective function to check whether we are minimizing or maximizing, right? Fitness function will tell you whether a particular fitness is good or bad, right? But objective function is going to optimize your things, right? Minimizing or maximizing. So that is one of the operator. Then this genetic representation is nothing but we are performing encoding or we are doing chromosome representation. That is a genetic representation. Third one is genetic operator, like crossover, mutations. These all are the operators coming under the genetic operator. Not only that, if you go for genetic algorithm, most of the cases you will find two popular operators are applied. One is called as crossover and mutation. Right? You can see here. There are three basic operators are there. One is called as crossover, another is mutation, and reproductions. But apart from these operators, there are a lot of operators are there, which we call as inheritance operator or low-level operators that you can apply, right? That you can apply to your particular problem, right? Like first one, if you see, one operator is called as inversion. As the name suggests, inversion means 0 is going to be changed to 1 and 1 is going to be changed to 0. Similarly, there is another operator called dominance. There is another operator called deletion. Suppose you want to delete 2-bit from a particular coding, right? Suppose you have a 10-bit representation. In 10-bit, you want to delete 2-bit of information. That is coming under deletion. Similarly, we have intrachromosomal duplication, translocation, segregation, speciation, migration, sharing, and mating. These operators are nowadays not seen in the latest variants of the genetic algorithm. But still, depends upon your research problem, you can apply these operators to your problem. Now, this is the flow chart of the genetic algorithm. If you see, we start with the process of initial population. Okay, initial population. Before initial population, you have to encode your chromosome, right? Suppose if you go for the process of encoding, right? Suppose you want to take 20 population. Like previously I told you, there are different solutions are there. Like here, you have to take 20 different solutions. They are your initial population. Then you apply the process of selection. Okay. So in the selection process, what happens? Some of the chromosomes are discarded. Some of the chromosomes are duplicated. Like out of 20 chromosomes, you assume that 5 chromosomes are the best performing chromosomes. 10 chromosomes are average chromosomes. Their performance is average. Another 5 chromosomes are worst performing chromosomes. So what we have to do? We have to discard these 5 worst performing chromosomes. And we have to take multiple copies of these 5 best chromosomes. So it becomes 10 and average becomes 10. So total again you have 20 population. So in the selection process you have 20 population only, right? But there are some, this 20 is not same as this for 20, right? Because you have discarded some of the populations. Now all the things are placed in the new population. So from new population onwards, the process of genetic algorithm actually starts. Now you can see once the populations are ready with this new population, then first you have to check the termination condition. Generally, termination condition we consider that after 30 iteration, whatever result you will get, will stop. Or after 50 iterations, whatever result we have to stop. So first we will check with the we will check with the termination condition, right? If the termination condition is satisfied, then you have to stop. If the termination condition is not satisfied, then you have to go to the process of crossover. Okay, you will go to the process of crossover. So what actually crossover is doing? Crossover is taking 2 different parents from the new population. Let us take P1 and P2 are the 2 different parents taken by crossover. Then after exchanging this P1, P2, after performing the crossover, then you will get C1 and C2, that is children 1 and children 2, right? So after performing crossover, you are getting children, okay? And once you get the children, you have to apply another operator that is called as your mutation. So mutation will give you modified children 1 and modified children 2. So this is modified children 1 and modified children 2. So after mutation, you will not mutation is not applied to your parent. Mutation is always applied to the children. So you will get modified children and modified children 2. Then you have to check the fitness of this modified children 1, modified children 2 with the parent 1 and parent 2. That you have to compare, right? Modified children 1, modified children 2, you have to compare with the parent P1 and P2. So here we are checking the fitness. If let's say parent 1 is performing, giving you good fitness, modified children 2 is giving fitness. So these 2 populations is going to be stored in the new population. Okay, so P1 is always there, P1 is already there, only modified children 2 is added into the new population by replacing the parent P2. Okay, earlier P1, P2 is there. Now P1 will be there as it is, but P2 will be replaced by modified children 2. Right? Now I'll check the termination because one condition is over, one iteration is over. So let's say my termination condition is 30. So till now I have not reached 30. I am in the iteration 1 only. Then again I'll perform the crossover. I'll do the mutation, right? Then checking fitness. So this iteration will be done 30 times. After 30 times, whatever values are there, that is going to be accepted, right? Now, let us see one by one step, whatever there in the flow chart. The same thing we'll discuss throughout this particular lecture. First one is called as creation of offsprings, right? So that is nothing but your source space. You are given with a particular source space. In that, you have to create your offsprings. Okay. So source space is nothing but the space for all possible feasible solutions. Like I told you, the problem of 16 to the power 512 number of solutions. So these are nothing but all possible solutions in the source space. And irrespective of the solution, suppose I am taking 5 different solutions. Okay, each and every solution is having a fitness value, right? It may be one fitness is good, one fitness is bad, but there is a fitness value you have for each and every solution. Now we are looking for a solution for this particular problem. A problem is given to you, you are solving using optimization method, right? So looking for a solution means looking for an extreme. Either you want to minimize, the maximum fitness you will find. If you want to minimize, then you will take the minimum value, okay, in the source space. So when the source space is very, very huge and it is too complicated, you cannot find the solution in your lifetime. And you also don't know where to look for the solution and where to start from. In that case, genetic algorithm or any optimization method you can apply to your respective domain. Okay, those cases your number of solutions are very, very small and very, very small. Don't apply the genetic algorithm in that particular domain. Now, let us take a on constant optimization problem. For example, there is a objective function that is f of x. Okay, if it is a maximization problem, what you have to do? If it is a maximization problem, you have to calculate maximum of f of x, right? If it is a minimization problem, you will calculate minimum of f of x, right? And the values of x is having a lower bound and an upper bound, right? Like we mentioned, -2 less than x less than equal to +2. So boundary we have fixed is -2 to +2, right? So if you want to minimize f of x, sometimes what happens? A problem is given to you that is a maximization problem. Sometimes you are given with a particular problem which is a minimization problem, but you want to convert the minimization problem, like minimize f of x, to a maximization problem, right? You want to minimize f of x, which is a minimization problem. You want to convert it into a maximization problem. So in that case, you will do maximize of 1 by f of x. But if you do maximize of 1 by f of x, in the denominator part, f of x is there, right? If f of x is equal to 0, then it becomes 1 by 0, which is not defined, right? That's why what we are doing, instead of writing 1 by f of x, we are writing 1 plus f of x. Okay, if f of x values are positive values or 0. But if the f of x values are negative, right, then you have to write maximize minus of f of x. So in this way, you can convert a minimization problem into a maximization problem. Now, let us come to the NAPSA problem, one of the very popular problem in computer science. Okay, in mathematics, you can say. So here, suppose you want to go to a shopping mall, and in that shopping mall, you want to carry, let's say, one bag, right? That is called as knapsack, right? So that bag has a capacity, right? You cannot exceed the capacity of that particular bag. So that bag, you can put any number of items subjected to it puts it below the capacity of that particular bag. So in order to represent this particular problem, each and every item is represented with a value as well as a size, right? Like if you consider I1 and I2, so I can say this is the value of this item, let's say 100 rupees. Size is, let's say, 200 grams, right? Value is, let's say, 500. The size is, let's say, 5 kg, something like that, right? So suppose in that shopping mall, if you have you can say there are 12 different items we have in that shopping mall. For a simplicity of example, So I can represent my chromosome with the 12 different cells. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? So this is for I1, this is for I2, this is for I3, up to this is for I12. So you have 12 different items. So if I'm writing 1 indicates that this particular item you are putting in your knapsack, means you are interested to buy this particular item. Like if you see chromosome A, you will find one, this one, this one. These all are you want to include it. So the things you want to put in the knapsack is represented as 1. If you want to exclude it, then that is represented as 0. That means you don't want to take that item into your or you want to put that particular item in your knapsack. So not only that, here the item is represented as a binary 1 0, or you can say 1 bit of binary. But in your respective problem, you may find you can put these strings in 4-bit binary, 5-bit binary. Suppose you will go for 4-bit, then you will get 2 to the power 4, 16 different items. If you represent 5-bit, then 2 to the power 5, that is 32-bit. So number of items is 16, then 4-bit is sufficient. If number of item is 5-bit, then number of item is 32, then 5-bit is sufficient for that particular problem. So here you can see we have taken 2 different variables. One is x1, another is x2. And the range of x1, if you see, it is all zeros to all 1. Similarly, the range of x2, you can see all zeros to all 1. The values may be in between any value, right? And each and every variable is represented in 4-bit, right? So if there are 12 items are there, 15 items are there, so you can say 0 to, let's say, 15. Okay, total 16 different items are there. First item you will represent it 40, then 001, then 0010. Like that, the last item is 41. Right? So not necessary you will start with the scale of 0 to 15. The scale of 0 to 15 is same as the scale of 2 to 17. That's why if your lower limit is 2 and the upper limit is 17, then you have to add the lower limit. Then you have to find the upper limit minus lower limit divided by 15 multiplied by decimal scale is 10. That means representing 1010. So if you put 8421 roll, it is nothing but 8 plus 2, right? That is 10. Right? That is equal to 10. Right? So now your lower limit is 2. So you have to add 2. So you will say it is 12. Right? So 12 is same as your 1010 because your lower limit starts from 2. So it is this 1010 points to decimal equivalent 12. But if your scale starts from 0, we represent that by the value is equal to decimal value 10. So it is not necessary to code all variables in equal substring length. It is always not recommended also that to code for all variables in the same length. First variable is maybe represented in 1 bit, second variable maybe 3 bit, third variable maybe 2 bit, and so on. Okay, now you can see this another problem. This is called as a representation of fiber angle in the form of binary encoding. So if you see here, there are 16 different codings you have starting from 0 to 15. You can say decorated values are 0 to 15, 4 zeros to 41. So first 0 represents fiber angle 0, 0001 represents fiber angle 10, 0010 represents fiber angle 2. So there is no need to code each and every in equal string length. Also, there should not be equal gap between each and every fiber angle. Like here the gap you can see that is 10. Here the gap is again 10. Here the gap is also 10. Here the gap is 15. Here also the gap is 15. Here the gap is more, right? So it is not necessary that it is equally distributed so as to apply the linear mapping rule, right? So in that way, various problems are having various type of representation, and their mapping is also different. Now, not only you are going to apply, you can say binary coding, but you can go for octal coding. You can go for hexadecimal coding also, right? For example, if you go for octal coding, you know octal means the values are in between 0 to 7. So for a particular value, it is 4 zeros to 47. So in octal 8, 9 is not there. Similarly, if you want to go for hexadecimal, x1 is going to be represented as 7 0 to 4n. Because hexadecimal means it may be 0 to 9, and again it is from A to F. Right? In this way, you can represent. So most of the research articles you can see they are using binary coding, but it is not necessary to go for binary coding. You can go for octal coding. You can go for hexadecimal coding as well. Now, if you go for permutation coding, like one of the very popular problem is called as a traveling salesman problem. In traveling salesman problem, a salesperson has to visit from one city to another city, and the start city is same as the end city, and each and every city should be traveled once, right? So if you go for chromosome with nine cities, so you can see one. If I do 2, 3, 4, these are the cities present in a particular map. Suppose, so you will start with city 1, then you will go to city 5. Okay, then you will go to city 3, then city 2, then city 4, then city 7, then city 9. Okay, then city 8, then city 6, then you will back to your city 1. So you can see in this particular solution, all these things, right? You can see all the cities are visited once, right? So it is a valid solution. But what happens if this in place of this 6, suppose I will put to 7. So 7 is already visited. Again, you want to visit 7. So it is an invalid chromosome. So in order to avoid this invalid chromosome, you have to go for genetic operator correction. Okay, genetic operator correction will help you to correct a particular bit, right? Like mutation also we are targeting a particular bit. Here also we want to put a particular bit. We want to correct that particular bit. Not only the representation is with respect to binary or you can say octal or hexadecimal, you can take a floating point number or double number as a chromosome value. Like here you can see a chromosome with 4 cells are there. So through which you can see these values are nothing but the floating point values, or these values are called as double values. Like here you can see another chromosome where you have a set of alphabets as the chromosome. Here you can see set of actions, like if you consider a robot. In robot case, we have 4 operations, right? One is forward, back, left, right. So you can use that also for these actions as a to represent in the form of chromosomes. Like many people are also working in the neural network where they want to update the weight of the neural network, because the weight is transferred from the input layer to the hidden layers, one hidden layer to another hidden layer, and the last hidden layers to the output layers. In that case, this type of coding is well suitable. Now, similarly, you can go for tree coding. In tree coding, we are using various set of functions and commands. We can use prefix representation, postfix representation, or you can represent in the form of different functions, right? Through which you can go also different type of coding, right? Like here you can see x plus 5 divided by y. 5 divided y can be written as divided by y. Then x plus can be represented plus x if you go for prefix notation. So this way also you can represent a particular coding. Now, initially, if you see, genetic algorithms are targeted for solving the maximization problem. Okay, they are not targeted for the minimization problem. But as you know, that minimization problems are transferred to the maximization problem by some suitable transformations, right? So if a minimization problem is there, that is f of x, if you want to transfer it to the maximization problem, you can write 1 by f of x, or vice versa is also true. But you have to ensure this f of x value is not equal to 0, right? If f of x's value is equal to 0, then you have to write 1 by 1 plus f of x, right? When f of x is equal to 0. In this way, you can convert minimization to the maximization problem or maximization problem to a minimization problem. Now, let us take a particular problem to understand the genetic algorithm. Like here you can see, I have taken a objective function f. That objective function f is equal to pi of theta 1 comma theta 2. Okay, theta 1 and theta 2 are nothing but theta 1, theta 2 are the nothing but the angles, right? So suppose the fitness function f is equal to minus 4 sine theta 1 minus 6 cos theta 1 minus 4 sine theta 2 minus 2 cos theta 2. So if I give the values of theta 1 and theta 2, you can tell me that what is the value of this objective function. Let us take theta 1 is equal to 0, theta 2 is also equal to 0. So if you solve this problem, you will get minus 4 sine 0, minus 6 cos 0, minus 4 sine 0, minus 2 cos 0. So you know sine 0 is equal to 0, sine 1 is equal to sine cos 0 is equal to 1, right? So this sine 0 is equal to 0. So entire term is 0. This is also 0, right? So 0 minus, and this is equal to 1, right? So 0 minus 1 plus 0 and minus 1. So it will return you the value minus 2, right? Sorry, this is minus 6 because 6 is there, right? So it's minus 6 into 1. So minus 6 and this is minus 2. So you will get, okay, minus 8. Okay, you will get minus 8. Now, if you take the fiber angle example, where I specified that the angles are in the between 0 to 90. Okay, the angles are in between 0 to 90. So, you know, if I represent in 4-bit binary, so maximum I can represent 16 different things. Suppose I'll divide each and every angle with 6 degree. So I'll write 90 divided by 15. So in each 6 degree, the code is going to be changed. Because I'll start with 4 zeros, then I'll go for 0001, then I'll go for 0010, 0011. First one represents 6, second one represents 12, third one represents, first one represents 0, second one represents 6, third one represents 12, and fourth one represents 18, and so on, right? So in each and every 6 degree, the code is going to be changed, right? And not necessarily you are going to do in that manner. If you represent in more bits, suppose I want to represent in 5 bits. So I have more scope, right? Suppose I want to take 90 divided by 30. So in each 3 degree, you will see the code is going to change, right? So it depends on you whether to take 4 degree or 3 degree or 5 degree, right? Now, if you see, this is the problem where you can see total 16 different codings are there. Each and every coding is 4-bit. So 4 zeros represent 0 and 4 ones represent 90. And you can see the difference between each and every coding. Although it is need not be equal to the uniform, okay, it may not be equally distributed. But for this case, luckily we are getting the difference of 6. Now, here we have seen the concept of objective function. So now we'll focus on the fitness function. Suppose the fitness function f is equal to f dash minus 7. And f dash is nothing but minus f of minus 7. Right? And f is nothing but your objective function. Right? Objective function means what you have seen. Minus 4 sine theta 1, minus 6 cos theta 1, minus 4 sine theta 2, and minus 2 cos theta 2, right? That is called your objective function, right? So if you solve this objective function by putting theta 1 is equal to 0, theta 2 is equal to 0, what you got here? You got the value as minus 8. So I can simplify it by writing minus of minus 8 and minus 7. So I'll get the value as 8 minus 7, which is equal to 1. So if I take theta 1 is equal to 0 and theta 2 is equal to 0, then I am getting the fitness function value as 1. Similarly, I can put theta 1 is equal to 12, theta 2 is equal to 6, then you will see fitness value we are getting is 2.10. Okay. Now, if it is a maximization problem, right? If I'm solving a maximization problem, okay, if I'm solving a maximization problem, which value is better? You can see highest value is better. Highest value is 4.66. So fifth population is better. And which value is which population is worst population? So you can obviously say the population 1 is the worst population because the value is 1, which is least among all the 8 different populations. So as a summary, what you can say here, objective function is the function that is going to be optimized, whereas fitness function is what that is used for guiding the optimization. So sometimes also we can take fitness function is same as our objective functions, right? So let us start. This is all about the initial population. Through initial population, you have to generate some random population and can estimate their fitness value. Once you are ready with that, what you are going to do? You have to apply the reproduction or selection operator. So selection operator is the first operator that is applied to the population. So here we have considered 8 different population. For these 8 population, we want to apply selection operator. And the above average strings are picked from the current population and multiple copies are inserted into the mating pool in a probabilistic manner. So once you calculate the fitness value, you can know that whether that string is above average or that is below average. If above average is there, that is written in the current population. If it is above average is there, if below average is there, that is going to be discarded from the mating pool. Okay, so see, there are different selection methods we have. We'll start with the roulette wheel selection, then we'll see the rest of the method like tournament selection, ranks selection or elitism, different selection methods we have. So if you go for roulette wheel selection, there is a wheel with a marker. You have to spin the wheel to know that where which population you have to pick from a mating pool, or which population you are going to select, right? That is depends upon spinning a particular wheel. So a string is selected from the mating pool with a probability proportional to the fitness. So see here, we know there are 8 populations. This is the binary coding of 8 different populations. Then the angle of these 8 populations, right? So the angle, first angle is 0, 0, right, which represents as 4 zeros, and is also represented 4, 0. And we have also calculated the fitness in the previous slide, which is nothing but minus f minus 7. So in order to calculate the probability proportion to the fitness, what you have to do, you have to consider current fitness. Okay, you can see current fitness divided by sum of all fitness. Sum of all fitness. So you can see for the population 1, the fitness is 1, and sum of all fitness, if you sum all the fitness, you will get 23.27. So you will get the value as 0.0429, and if you percentage wise, if you show, it is 4.29%, which is equivalent to 5%, right? Similarly, if you go for population number, let's say 8, okay, population number 8, if you choose, right? So it is 4.55 is the current population divided by 223.27. So you will get 0.1955, which is nothing but 19.55%, which is equivalent to your 20%. So if I take a wheel, first population takes 5%, and the last population is going to take 20% in the wheel. So see this way, you can see easily the first population takes 5% of the area of that particular wheel, and the 8th population takes 20% of the wheel. And there is a marker here, right? So when you spin this wheel, so after some time it is going to point to a particular population number. Okay, so obviously if a particular population holds maximum area, then there is a more chance that that population is going to be selected, right? So apart from that, in order to incorporate this one, which population is going to come, we have to calculate the cumulative probability. You know, cumulative probability means you will consider the probability of the previous population plus your own probability, right? So here we'll see the details about the cumulative probability. And now till now you know what is population number, you know population's probability pi, right? Now talking about column A is nothing but the calculation of the expected count. And expected count is calculated by multiplying the probability with 8. Like here you can see the probability is 0.0429. If you multiply with 8, you will get the value as 0.33. Similarly, 0.1955. If you multiply with 8, you will get the value as 1.56. Right? Now, once you are done with this expected count value, the next column what you want to calculate is called as cumulative probability. So cumulative probability of the first one is, if you see here, this is the probability column. If you calculate cumulative probability, the same thing will appear here. But when you go for the second population, it is nothing but 0.0429 plus 0.0900. So 0.1329 will come, right? Similarly, if you go for third population, you have to add 3. If you go for the fifth population, you have to add all the previous 4 population and current populations. So you will get the value at 0.6388. Now, once you are done with this cumulative probability calculation, the column C is generated by taking random values. Okay, you can see the column C. Column C, we have generated the random values in the range of 0 to 1. So if you are, if you know about MATLAB, a programming tool. So in MATLAB tool, if you go and write RAND, okay, then it is going to generate a random number in the range of 0 to 1. Okay, so such type of random functions you can use to generate the values in the range of 0 to 1. Now, if you go for column D is going to, you can say it is going to check that whether the column C value is in the range of population 1 or population 2 or population 3 and so on. Like here you can see the value is 0.259. So we have to check whether this value 0.259 is in the range of, you can say it is in the range of 0 to 0.0429 or in the range of 0.0429 to 0.9 or in the range of 0.9 to 0.1336 or in the range of 0.1336 to 0.1723 or so on. So if you see 0.259, okay, this is 09, sorry, this is 09. Okay, so 0.259 is lies in the range of, you can see here, 1336, okay, 1336, no, just a minute, I've done a wrong calculation here. So if you see, you have to check the range, that is 0.0429, 0429, you have to see column B, not the this PI column. Okay, then you have to check 0.0429 to 0.1329, 0.1329 to 0.266. These are cumulative probabilities, right? 266 to 0.438. Now, 0.259 is in the range of this particular population. That's why the population number is written there as 3. Similarly, if I ask you 0.038, okay, 0.038, it is in the range of this one, right? So we have written the value as 1. Yes, if you have any doubt, you can ask. Is there any doubt? Okay, there is no question like that. You have to find the values for a D Once you are ready with all the values of D, the next one you have to do calculation the value of E. So you will see in the column D how many times 1 is repeated. So 1 is repeated one time, so the best value is 1. 2 is repeated one time, that's why value is 1. 3 is repeated one time in this column. 4th is repeated twice, so I'm writing the count is 2. 5th is repeated 2 times, the count is 2, and so on. And you can see 8 is repeated one time. So you can see in this particular column, the population number 6 and 7 is not repeated at all. As the population is not repeated at all, so you have to discard the population 6 and 7, and the population 4 and 5, it is duplicated. That's why I told you, if you enter with a selection phase with 8 population, in the output also you will get 8. But the difference is that those population you will get, that is not same as the previous populations. Right? Now, there are two issues related to the ruler till selection. The first issue is related to the population diversity, which says that the genes that are already discovered as good individuals are exploited. Obviously, like here in the previous case, you have seen the population, you can say 7, right? Which population? Yeah, population 4 and 5. These populations are duplicated, and the population 6 and 7 is discarded, right? So those populations are good individuals, they are exploited, while promising the new area of the source space continue to be explored. That says population diversity, but such type of issues are there in the genetic algorithm. Coming to the second issues, that is called as selective pressure, which says that it is a degree to which the better individuals are favored, right? So yes, so in the selective pressure case, if there is high selective pressure, then convergence rate is very, very high. But if there is a low selective pressure, then again the slow convergence rate you will find. So you have to balance these two, right? So you have to see that you need not reach to your solution is not reaching to the local solution. Okay, if you will go to the local optimal solution, then your you will not achieve the solution that reach the global solutions, right? So these are the two issues we are finding in the ruler till selection. Coming to the second selection method, which says that the tournament selection, what we are doing in tournament selection, we conduct a series of tournaments between the populations, and based upon the fitness value, we declare that one of the team won a particular match and one of them is losing a particular match. For example, I have randomly selected 2 population out of this 8 population, and I found that the fitness value of 2 is 2.10, fitness value of 4 is 4.01. So if you see best fitness value you are getting in comparison to these two is your population number 4. So you have to declare 4 is the winner of this particular match and 2 is the loser of this particular match. Similarly, we conduct with 3 and 8. 8 is the winner, 3 is the loser. We conducted 1 and 3. We found that 3 is the winner and 1 is the loser. So after conducting a series of matches like 4 with 5, 1 with 6, 1 with 2, 4 with 2, 8 with 3, we found that 2, 3, 5, 6, they are having only one match they have won against their opponent. And 4 and 8 are the populations they won twice against their opponent, and 1 and 7 are not chosen at all because they lose all the matches. So what we are going to do, the population 1 and 7 is going to be discarded and 4, 8 population is going to be duplicated, right? So again, you have 8 population before selection, 8 population after the selection process. But in this 8, 1 and 7 is not there, and 4, 8 is duplicated twice. So if you compare with the ruler till selection, then 6, 7 is omitted in the previous case, and here 1, 7 are omitted. But rank selection has some advantages over your ruler till selection, because if you see the first one, if you go for ruler till selection, if a particular population occupies 75% of the space, so maximum chance whenever you spin the wheel, the population 5 is going to come. In order to avoid this problem of roulette wheel selection, we have a rank selection method. So after finding the probability and percentage, we see which population is having highest percentage, and we give that population as highest rank. And if a particular population is having lower percentage, we give lower rank to that particular population. Then we calculate the percentage by taking the current rank divided by sum of all rank. So for this we have calculated 1 by 15. For this we have calculated 5 divided by 15. So these are the values we are getting as a percentage. If you represent in the form of a wheel, it is a better representation in comparison to the roulette method. That's why rank selection method is used in comparison to the roulette selection method. There is another method that is called as elitism, which says that the best and few best chromosomes are to be copied to the new populations. If someone is performing good, then you have to consider it. If someone is not performing good, you have to discard it. So this method was proposed by Goldberg in 1989, and he suggested that the fitness of ith individual must be subtracted from a large constant. So if fitness value is subtracted from a very large value, definitely the value is a non-negative value, right? And if you are dealing with a minimization problem, the new expression of fitness you can calculate as the sub fmax minus fmin minus of fi of x. And if fi is positive for maximization problem, then phi I is equal to your fi, right? So let us take an example to understand how actually elitism work. So we have taken 8 different population and their fitness value. Then we have calculated the current fitness divided by average fitness. If you calculate the average fitness by taking sum of these fitness divided by 8, you will get the value as 2.908. And if you divide the current fitness divided by the average fitness, you will get the value as 0.380. Here you will find 2.10 divided by 2.908, you will get 0.812. Here you will find 3.11 divided by 2.908, you will get 1.203, and so on. And if you look into this particular column, and if I ask you which population is performing better, then as it is a maximization problem, you will say population 5 is performing better, and population 8 is performing second better, you can say, next to the better one. And which population is performing worst, then you can say population 1 and population 6. That's why the population 6 and population 1 is discarded, and population 5 and 8 is included in the mating pool. So the overall objective of this one is the worst fitness is going to die, like the way 1, 6 die in this particular situation. There is another concept that is called as generation gap, or called steady state placement. Like over the iterations, what we are doing, we are actually replacing the different chromosomes. So if you want to calculate the generation gap is nothing but number of individuals that will be replaced divided by population size. Suppose I have taken 8 different population and 2 individuals are replaced in a particular round, then or iteration, then I can say it is 25%, right? So over a particular over a period of iterations, you will see the chromosomes are updated, means they are close to the global optimal solutions. There are some other methods are also applied here, like how you are going to select the parents, or how you are going to make the replacement. For that, there are many schemes have proposed in the literature. It may be selection of parent according to the fitness value, selection of replacement based on random, right, without looking into any particular order. Similarly, selection of parent can be done random and selection of replacement done inverse fitness wise, or both parents and replacement can be done based upon the fitness or inverse fitness. In this way, you can apply the selection method to the initial population in order to get new population. After new population, you reach to new population, we check the termination condition. If the termination condition is not satisfied, then we start the process of crossover. So the idea of the crossover is not to not creating the new one, but to exchange some part of the chromosome, first chromosome with second chromosome with first chromosome in order to generate the child. Like here you can see, in order to perform the crossover, you require cross site point. You need two different parents selected randomly. Like here you can see, I have taken two different populations. One is A, another is B. So here, suppose I'm choosing the cross site point is here. So I'll take the first part of A and second part of B. Then I'll choose first part of B and second part of A. In this way, I'll make the cross site. So the first children is 1 1 0 0 and the second children is 0 0 1 1. So this site of cross site is called as single site crossover. In single site crossover, we select a cross site point, take the first part from parent 1, right? You can see here, and second part from parent 2. Similarly, we can take first part of parent 2 and second part of parent 1. We call that as a child 1 and child 2. That is called as a single site crossover. You can go for multi-site crossover. Again, multi-site is divided into two parts. It may be a 2-point crossover. It may be a multiple point or more than 2-point crossover. If you go for 2-point crossover, instead of having only one cross site, you have more than one cross site. Like this is one cross site, this is another cross site. So I am taking the first part of parent 1, second part from parent 2, third part from parent 1. Similarly, I am taking first part of parent 2, second part of parent 1, third part of parent 2. In this way, you can generate two different children using 2-point crossover. Similarly, if you go for multi-point crossover, it is again of two types. You can go for even number of cross sites or you can go for odd number of cross sites. Even number of cross sites applicable to a ring. If I take a ring, if I ask you where to start or where to stop, there is no process, right? So I have to start from an arbitrary point. I have to stop from an arbitrary point, right? Okay, so if you go for a ring, right, where cross sites are selected around the circle uniformly at random. So this is your parent 1, parent 2. I'm taking the first part from parent 2, second part from parent 2, first part from parent 1, second part from parent 2, third part again from parent 1, and fourth part from parent 2. So you will see, you will get a child 1. So if you take the opposite one, you will get the child 2. Similarly, you can go for odd number of cross sites. In odd number of cross sites, it's just like a line. So you can see this is cross site 1, cross site 2, cross site 3. It is a odd number. So I'll take first part of the parent 1, second part from parent 2, third part from parent 1, fourth part from parent 2. In this way, I can generate the children using the parent 1 and parent 2. There is another crossover that is called as uniform crossover. Here, whether you have to take the value from parent 1 or parent 2, that is based upon the probability. Obviously, the probability is 0.5. Like here you can see, those persons are marked with this symbol. There you have to flip. Like for example, here I have to take parent 1 value to the child 1, parent 1 value to the child 1. When this interchange there, I'll take parent 2 value to the parent 1, parent 2 value to the child 1. Similarly, here parent 1 value to child 1. Here there is an interchange, so I am taking parent 2 value as child 1 and so on. So we select the parent 1 and parent 2 with a probability of 0.5. Similarly, if you go for another variant of uniform crossover, here we mentioned the crossover mask. Crossover mark says that it is a series of zeros and one only. If crossover mark is one, then child is going to copy from the parent one. If crossover mark is zero, right, then it has to copy from parent two, right? Here also it is zero, so it is taking from parent two. Here it is one, means you will take from parent one, and so on. Like that way, you can generate one children, and if you follow the reverse process, you can get the children two. Like if I take the crossover mask, zero means parent one and one means parent two, or if I flip parent one and parent two, then I will get another offspring. Now you can go for matrix crossover also, especially those people who are working in computer vision application or image processing application. There you can apply two-dimensional crossover. In two-dimensional crossover, what we are doing, we are taking one part from parent one cell from parent one, second cell from parent two, third cell from parent one, fourth cell from parent two. Either in the row measure order or in the column measure order, you can take the features from parent one and parent two for creating child one and child two. But according to Dave in 1999, he suggested that it was difficult to generalize the optimal crossover operator selection. If I ask you that which crossover is going to perform better, then there is no answer for it. Whether to apply single point crossover or multi-point or matrix crossover, there is no conclusion that which crossover will give you better result for your respective problem. Similarly, there is another concept that is called as crossover rate. Crossover rate says that how many crossovers you want to do in a particular iteration. Like if your population size is in between 30 to 200, you can take the crossover rate as in between 0.5 to 1. For example, we have considered 8 population in our example. Suppose you want to perform 4 crossover in each and every iteration. So the number of pairs that to be crossed is 4 and fixed population is 8. So it is called as 50%. Or you can take 8 pairs as well. If I divide by 8, it is 100%, right? So your probability should be 0.5 to 1. Although it is recommended to 30 to 200, if you apply for small set also, you can make 4 crossovers or you can make 8 crossover also. So yes, obviously, if you are taking 0.5, 50% remain same and 50% are altered in your population. There are some other operators that you can apply that is called as inversion. Inversion says that you have to choose 2 cross sites and 1 is flipped to 0 and 0 is flipped to 1. Okay, so a string from the population is selected and the bits between 2 random sites are inverted. So in that way, inversion works. There is another method that is called as deletion. So you have to choose some point and that particular point you are going to delete. Okay, and you can regenerate also, right? You can either regenerate a new bit or you can copy whatever there in the previous 2 bit. The same thing you want to copy here. That is called as deletion and regeneration or deletion and duplication, right? That you can do. Another operator is yes, deletion and regeneration. I have deleted all the bits that are available between 2 different cross sites and I have regenerated, right? 1101 is regenerated here. Similarly, there is another is called segregation. Here also you have to choose 2 different points. You will take the parent 1 value as it is, but you will take the parent 2 value to the child 1. Similarly, you will take the first part of parent 2 to the child 2, second part of parent 1 to child 2. So the bits of the parent are segregated here and then crossed over to produce the offsprings. It is also, you can say alternatively, it is same as single point crossover. There is another crossover that is called as crossover followed by inversion. So if these are the two parent, this is parent 1 and this is parent 2, in order to generate the children, I have taken two different cross site. So first part, then this part, then this particular part. Then I have taken first part of parent 2, second part of parent 1, and third part of parent 2. Right? So this is called as your children 1 and children 2. That completes the process of crossover. Then you have to perform inversion. Inversion means this 1100 is now changed to 0011 and 0110 is now changed to 1001. What we did actually, we did crossover. After that, we applied the process of inversion. But irrespective of this crossover, whatever we have discussed, single point, multi-point, any point a crossover, right? You will see if in a set of population, if the first bit is 0, except regeneration case, if first bit is 0, suppose I have considered these four populations, P1, P2, P3, P4. If the first bit is 0, you apply any crossover without regeneration, you will get the value is 0 in that children population. So the value will never change to 1 in the process of crossover. Okay, so as all four bits have a 0 in the leftmost bit position, irrespective of the crossover, you will get the first value is 0, which is not good. So as a solution, what you want to do, you have to apply the process of mutation, right? So what we are actually doing in the mutation, we choose a particular bit and we flip that bit. Okay, so this bit is earlier 0, so now I have changed to 1. But while you are flipping, as it is generated randomly, you may get the same value as well. As this value is 0, you are generating the random number in between 0 and 1, but you are getting the value as 0, right? Similarly, not only that, if the real number values are also there, you can regenerate it, like minus 69.4 is changed to minus 67.5. If you talk about the mutation probability, the mutation probability is in between 0.001 to 0.5. Okay, that is the mutation probability. Okay, so for example, if you take 8 populations, then you can do at max 4 mutation. If you forget about this particular range, right? That is nothing but 50%. 50% means 0.5 population, right? Now you can also apply other operator, like one is bitwise operators are also you can apply. Like if you go for one's complement operator, 0 is changed to 1, 1 is changed to 0. You can also go for bitwise AND operator, right? Bitwise AND or bitwise exclusive OR operator. If you go for bitwise AND operator, if both bits are 1, then only the output is 1. Otherwise, the output is 0. Similarly, if you go for bitwise exclusive OR operator, then you can say if both bits are same, then only the output is 0. Otherwise, the output is 1. Similarly, if you go for logical bitwise operator, one of the example is your bitwise OR operator. In that case, only case that is false, that is if all the values are 0. If parent 1, parent 2 is 0, then only it is 0. Otherwise, you will get the value as 1. Similarly, you can go for left shift and right shift operator. Left shift operator, suppose I want to left shift by 2. So this one is this 0 is going to come here, this 1 is going to come here, like this it will come, and the last 2 digit is regenerated as 0 or 1. Similarly, right shift operator case, if I right shift with the 2 bit, I will get like this, right? And I'll get like this, and these 2 bits are going to be regenerated. Okay. Okay. So if you talk about overally how actually this algorithm works, suppose I'll take another example here. Like I have taken an objective function. Let's say the objective function is to count the number of ones, right? If you see the first population, the number of ones is 3, right? Out of 10 bits, the number of out of 10 bits, the number of ones is 3. So you can say fitness is 3 by 10, which is equal to 0.3. Similarly, if you see the last one, the number of ones are 9 divided by number of bit is 10. So it is 0.9. So if you see these fitness values, you know the fitness of the first value is poor and the fitness of the last one is good. So I can take multiple copies of the last population and I can discard the population P1. So if you go for the Darwinian theory of survival, it suggests that the strongest individual have two copies, okay, and the average individuals having one copy and weakest individual have zero copy. Here the weakest individual is P1, that's why it is having zero copy, but strongest individuals, that is P4, that is having two copy. Average individuals, that is P2 and P3, they are having only one copy. In this way it actually works. And after generating the fitness and replacing the population which is the strongest population for multiple times, you can go for the process of crossover. So if you go for the process of crossover, suppose I want to do crossover in between 4 and 1, and the crossover points are 1 and 5 respectively. So this is the crossover point and this is another crossover point. So what I'll do, I'll take the first part of this one, second part of this one, third part of this one, which is represented here in the population P1. Similarly, I can take the first part from here, second part from here, third part from here. So I can call that as population number 4, right? So now after performing crossover, you can see the fitness is improved, but we have to do the mutation. After that only you can do the comparison. In the mutation, what happened? I have taken the 6th bit of the string 2 as 1 and first bit of string 1 as 1. Right. So 6th bit of string 2 is considered as 1 and first bit of string 1 is considered as 0. It is not 1, 0. So after that, you can see the fitness is updated as 0 0.9, 0 0.7, 0 0.9, 0 0.5. Now the weakest individual is your the 4th population, and strongest one is your population number 1 or 3, right? Now here we consider the mutation probability is 0.05, that is nothing but 2 out of 40 bits are muted. Okay, this is the process of generation cycle. If you carry out this complete process, whatever we have discussed, finally you will get, this is the mating pool which will be available for the next iteration. And this process is continued several times in order to achieve the results that is close to optimal solution. Like in this case, we have considered the crossover probability is 100%, but mutation probability we have considered only 2, right? 2 means it is 3%. So this is the complete cycle of genetic algorithm which we have discussed in this session. And if you want to go more about this one, I request you to refer this particular particular book, which is published by PHI Learning Private Limited. A very nice book discussed about the genetic algorithm. In fact, the slides are also part of this particular book. And if you want research article, you can refer this article. It's a nice article in the field of wireless sensor network to solve the load balance clustering problem. It is published also in a good journal, having good citations also. So you can refer this paper. You will know more about the genetic algorithm. Okay, thank you everyone. If you have any questions, you may ask.